Let's consider a network of SDN switches, such as open-flow switches, and a controller that is controlling those switches. And let's assume that we would like to write a program using this interface. We can think about this programming as proceeding in 3 steps. The first is that the controller needs to read or monitor network state as well as various events that may be occurring in the network. These events may include failures, topology changes, security events, and so forth. The second step is to compute the policy based on the state that the controller sees from the network. This is effectively what we talked about last time as the role of the decision plane in deciding what the forwarding behavior of the network should be in response to various states that it reads from the network switches. The third step is to write policy back to the switches by installing the appropriate flow table state into the switches. Consistency problems can arise in 2 steps. First, the controller may read state from the network switches at different times, resulting in an inconsistent view of the network-wide state. And second, the controller may be writing policy as traffic is actively flowing through the network, which can disrupt packets along an end-to-end path or packets that should be treated consistently because they are part of the same flow. Both reading and writing network state can be challenging because open flow rules are simple match action predicates, so it can be very difficult to express complex logic with these rules. If we want to read state that requires multiple rules, expressing a policy that allows us to read such a state can be complicated without more sophisticated predicates. For example, let's suppose that when we are reading state, we'd like to see all web server traffic except for source 1234. Simple match action rules do not allow us to express such exceptions. As a solution to this problem, we need a language primitive that allows us to express predicates. Here is a simple statement that has several predicates, such as and not. A runtime system can then translate these predicates into low-level open-flow rules, ensuring that they are installed atomically and in the right order. Another problem that arises is that switches only have limited space for rules. It's simply not possible to install all possible rule patterns for every set of flows that we'd like to monitor. For example, if we'd like to count the number of bytes for every source IP address and generate a histogram with the resulting traffic, we would potentially need a flow table entry for every possible source IP address. It's simply not possible to install all of these possible rules. The solution is to have the runtime system dynamically unfold rules as traffic arrives. A programmer would specify something like a group by source IP address, and the runtime system would dynamically add open-flow rules to the switch as traffic arrives, thereby guaranteeing that there are only rules in the switch that correspond to active traffic.